Hi, everyone, and thanks for joining me today for episode 773 of People Behind the Science. Today, we are resharing our interview with our guest, Dr. Amy Mainzer. Listeners, Amy is an infrared astronomer. She studies the universe using wavelengths of light that are longer than those that we can see. Infrared astronomy is especially useful for looking at objects that are relatively cool in temperature, such as asteroids. And in our interview, Amy shares some fantastic stories from her life and her research. So, listeners, I hope you enjoy this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of People Behind the Science. Today, I am excited to introduce you all to Dr. Amy Mainzer. So thank you so much for joining us, Amy. How are you today?
I'm doing great. Thank you for having me on the show.
Well, thank you for joining us today. I'm excited to tell our listeners just a little bit about your background. So I'll start by your current position. Listeners, Amy is a senior research scientist and the principal investigator for the Near-Earth Object Wide Field Infrared Survey Explorer, or NEOWISE, mission at the NASA Jet Propulsion Laboratory. She's also the principal investigator for the Near-Earth Object Camera, or NEOCAM, mission proposal, and the deputy project scientist for the Wide Field Infrared Survey Explorer mission. And now, after earning her bachelor's in physics from Stanford, Amy accepted a position at the Lockheed Martin Advanced Technology Center. She then returned to academia to earn her master's in astronomy from Caltech and her PhD in astronomy from the University of California, Los Angeles. Now, listeners, Amy has received many awards and honors for her work, including the Lew Allen Medal for Excellence, as well as the NASA Exceptional Achievement and Scientific Achievement medals. She's also been recognized, along with her NASA team members, for their efforts on the Spitzer, WISE, and NEOWISE missions. And listeners, Amy is here with us today to tell us about her journey through life and science. So Amy, today we want to get to know you as well as your science. So can you start off by telling us what you like to do when you're not doing science?
Okay. Well, let's see. Lately, one of the things I've been doing is roller disco, actually.
Really? This sounds wonderful.
It's actually really fun. I tried to find a hobby that was exactly not like what I do professionally, and this is pretty much it in a nutshell. Turns out there's a fairly large group of people for whom roller skating really never died out. It's terrific exercise, and it's a lot of fun, and I'm really glad that a friend of mine got me into it. It's one of the best ways to just completely forget about everything and have a good time and get outside.
Gotcha. Well, this sounds fantastic. A great way to escape from the science for a little bit. But that's what we're going to talk about next, Amy. So can you tell us now how you describe what you do to someone who might not be familiar with your field?
Sure. Well, I'm an infrared astronomer, and that means basically I'm studying the universe using infrared wavelengths. So these are wavelengths of light that are longer than what your eye can see, which is visible light, of course. The thing about infrared astronomy is that it basically allows us to look at things with a whole new point of view. It's very good for sensing things that are particularly cool, because essentially what we're doing with infrared is we're sensing heat from objects in a lot of cases. So if things are particularly cool, they show up brightly at infrared wavelengths, even if they're dim at visible light wavelengths. And that's useful for a lot of things, like, for example, looking at asteroids. And that's one of the things I've been studying pretty actively now for a while with our infrared telescopes.
Well, this is fascinating work. I always love chatting with people from NASA, and I'm excited to dive into the details of your research as we go through the interview. But Amy, let me start by asking you about inspiration and motivation. I know these are things that are perhaps never in short supply for scientists. They're always very motivated to work on their research questions and get a lot of exposure to inspiring people throughout their careers. So can you share with us what you might consider one of your favorite motivational or inspirational quotes?
Okay, never give up, never surrender.
I like it.
It's from Galaxy Quest, so that's one of my favorite movies.
Well, that right there is motivational and inspirational right there. So how does this apply in your life, or how do you use this on a daily basis?
Mostly I think that's one of the funniest movies, and every time I see it, it cracks me up. But, there is something to the notion that you really do have to be pretty persistent to be in science, because a lot of what we do is write grant proposals, and that means we're constantly getting rejected because the success rates for a lot of our proposals are pretty low. So persistence is an important quality, I would say, but also really trying to hone in and make sure that what you're trying to answer is, in fact, one of the more interesting questions, and can you really refine it to be something that is worth spending significant time and resources on?
Definitely. Well, I think that is a fantastic quote to use in life and science. So thanks for sharing that with us today. And I'm curious next to hear about some of the people who've motivated or inspired you over the course of your career. Can you tell us about some of these people who've been role models for you?
Oh, definitely my mom. She's not a scientist. She's actually an artist, but she's always had just an unfailing interest in nature. And she's a very curious person. She loves to learn things. And that really, I think, was sort of the single biggest inspiration to me, was just being around somebody who was interested in things and who never forgot how to be curious and fascinated by nature. It doesn't really matter if you have somebody in your life when you're a kid who's a scientist. You don't really need that, in my opinion. You just need somebody who's supportive of you and who likes to ask questions and likes to listen to you, try to answer it yourself. That was really inspiring. And then in terms of my professional career as a role model, I'd say a woman named Professor Judy Pfeiffer. She's an astronomer at the University of Rochester. She's really one of the pioneers of infrared astronomy, and she's been kind of one of the main forces, I would say, in taking the infrared detectors that we need to be able to see the universe at infrared wavelengths from their original state, which was basically single pixel cameras, just one pixel, handmade at a time, to modern-day megapixel arrays. Nowadays, we have infrared arrays that are basically similar in form and function to the camera chips that are inside our cell phones. They're megapixel format. And with these, we can make very efficient maps of the universe, even at infrared wavelengths. Judy was really instrumental in bringing that to fruition.
Well, very interesting to hear about some of these people who've had a big role in your life. And I think early on, you brought up a great point that you don't need to have scientists all around you in order to become curious about the world, in order to become a successful scientist. And I myself was in a similar position. Neither of my parents were scientists. I didn't really know any scientists growing up, but I had my father, who was always sort of Mr. Fix-It, trying to figure out how things work, asking questions, asking me a ton of questions I could never answer. And also my mom, who was really interested in how the world worked. So I think having those people around you who are just curious really helps ignite that curiosity. So then take us back a little bit. You talked about how your mom was an inspiration for you as a kid. When did you turn from this general interest in nature to maybe looking towards space and astronomy?
Well, for me, it happened when I was pretty little, and I was about maybe 6 or 7. And I remember I had kiddie books on Greek mythology, the legends of Andromeda and Perseus, things like that. And I just loved those when I was little. I remember reading those books really, really eagerly. And at the time, of course, one of the things we would do is we would look in the encyclopedia if we wanted to find something out. And I remember looking in the World Book Encyclopedia, looking up definitions for some of the mythological characters. And they all have multiple definitions. So if you look up Andromeda, you get the mythological character, but then on the next page, you also get this picture of a beautiful galaxy. And I remember pretty distinctly actually looking in those pictures and thinking, wow, this is really interesting and pretty and cool, and I want to learn more about that. So that really kind of set me on the path to being interested in the universe. And after that, that is really what I wanted to pursue, and I kind of stayed on that. But I was always interested in lots of areas of science, and I think that's one of the great things about being a scientist is that just because we specialize in one particular area, you can kind of carry that sort of attitude and curiosity and wonder to all kinds of different areas and fields. So even though I study astronomy professionally, I love learning about all kinds of things like marine biology and plant biology, birds. There's always something to learn, and it's really fun.
Definitely. And I know I myself sort of really struggled when I was trying to pick a scientific field to specialize in, because I was the same way. I was like, well, marine biology is awesome. Like, I want to learn about this. And I also want to learn about this, kind of pulling me in all different directions. So what finally made that decision for you? I mean, you mentioned being interested in the galaxy and stumbling across this encyclopedia article. How did you, as you were starting to take your classes and get more involved in the career pathway, what kept you on that path?
It was kind of a strange journey a little bit. I mean, I really loved astronomy as a kid, and I just kind of stayed in love with it. And at some point, somewhere along the line, it occurred to me that if I wanted to keep studying astronomy, that I needed to learn more about math and physics. I just remembered at high school, at that point, you really have to start thinking about what are you going to do for college. Mm-hmm. You're going to go into astronomy. And I remember reading in a book that I had that astronomers tended to go and have PhDs, and that sounded really daunting. I didn't know any astronomers. I hadn't met any. somehow I figured out that, okay, I need to go to college and I probably need to major in either physics or astronomy. And then after that, I need to go on to graduate school. When you're a kid in high school, that looks pretty intimidating, but I just sort of hacked away at it and kind of kept that. It was sort of a guiding light, so to speak. I guess if I had known how hard it would be, maybe I wouldn't have done it. But at the same time, I just thought, well, let's give it a try. And well, that's what happened.
Very cool. Well, I love this sort of keep moving forward mentality. And I think it is daunting when you're looking at the career pathway. And I think particularly now for people who might be in high school or undergraduate thinking about a career in science and thinking, okay, have to make it through college, have to make it through graduate school, 1 or 2 postdocs, looking at the career trajectory, you've got your next 10, 15 years planned out already. So, but I think that passion, that curiosity is what drives people through it. So very cool to hear about your experiences. And now, so tell us a little bit about, we mentioned in our introduction that you took a year off after college, perhaps figure out what you wanted to do, and you ended up working at Lockheed Martin. Can you tell us about that experience?
I was originally planning to go straight to graduate school, and I actually had my graduate school admissions. I had a fellowship all lined up and everything. I wasn't really planning to take any time off at all. I was really just going to follow the traditional path and go straight from undergraduate to graduate school. But what happened was I had some engineer friends, and they were going to a job fair. So I thought, maybe I'll go with them just for practice, just to see what happens. And I made a resume because I thought, well, that would probably be just a good thing to do in general. Mm-hmm. So I took it and I passed it out at the job fair and wound up with a job offer from Lockheed Martin. And that was really unexpected. I really wasn't expecting to go in this direction at all. But there were some practical considerations. Namely, I had no money.
Right.
When I finished college, I was really broke, and the thought of moving to Southern California without having a car was kind of intimidating. And I thought, well, I could maybe take a job and just work for a little bit and gain some experience and save up a little money and buy a car, and that might make graduate school easier. It might be a little more of a practical thing to do. So I thought, well, what the heck? Let's try it. And so I was able to defer admission for a year with my fellowship and with graduate school, and I started at Lockheed. As it turned out, that was a key decision that really was a turning point for the whole rest of my career, because the project that I wound up working on at Lockheed was not any ordinary spacecraft. It was the Spitzer Space Telescope, which is a NASA infrared space telescope. And it was just so clear the minute I landed on the project that this was going to be really special, and it was going to do great things. I really wanted to learn more about it, because at that point, I was pretty sure from my college work that I wanted to do astronomy. But I knew, because I had worked in a lot of laboratories in the physics department, that I really wanted to do something experimental and hands-on. I wanted to build instrumentation that would be used for astronomy. Mm-hmm. So this was a perfect opportunity to basically build a space telescope that would be used by astronomers all over the world to do all kinds of interesting things. And this was a way of basically getting in and being able to build part of it with my own hands. And I thought, this is really special. I need to try this. It was a great decision.
Very cool to hear about your experience. And I think this is a position, a juncture that a lot of students are finding themselves in now. You finish college or you finish graduate school and you're kind of trying to figure out what to do next. And I think opportunities come from unexpected places sometimes. And sometimes you have to be willing to give them a chance, and you never know where they might lead. And I think this is a perfect example of that. So then tell us how you transitioned then from Lockheed, then going into graduate school, getting your PhD. How did you land that position at NASA?
Well, it was a bit of a struggle at times. I mean, there's no question about that. It was a really amazing experience, though. I wound up working on the fine guidance sensor for this telescope. And this is basically a small camera that steers the telescope, essentially. It tells it where to point. And this was a great opportunity because getting to build this camera was something that you normally don't get to do, especially if you're a graduate student. They don't let you near.
Right.
Usually you don't.
They don't trust us.
Yeah. Usually you don't get to be, handling flight hardware, let alone putting it together and integrating and testing it and all of that. So that was a pretty amazing experience that I would have never had if I hadn't been at Lockheed. Because there, just as one of the staff engineers, it was assumed that of course you were going to design flight hardware and of course you were going to build it and test it, finish the job and deliver it successfully. So that was a really wonderful thing. They really put a lot of trust in me, and I always very much appreciated that. And also that carried through to my work in graduate school, because at that point when I came back to graduate school, I had a lot more experience than a person normally would. And that made it a lot easier for me to do my thesis project. So I started off and did my graduate school classes and took the qualifying exams and all of that. And then I transferred to UCLA because I really wanted to work with the infrared astronomy group there. And by that point, having seen what Spitzer was going to be able to do for infrared astronomy, I really wanted to work on that scientifically. So I was able to join a lab there that was doing something very similar to what I was interested in. And I there was able to work on another camera, another infrared instrument that was destined for an airplane, actually, for an airborne observatory the Stratospheric Observatory for Infrared Astronomy.
I like the names. Yeah.
Yeah, long name. It's called SOFIA. It's the Stratospheric Observatory for Infrared Astronomy. So this is a much larger camera physically than the one I had built for Spitzer because, of course, for space, everything has to be very tiny and compact, whereas this airborne observatory was just for a much larger telescope. So that was a lot of fun. It was hugely challenging, and the connections that I had made working for both of these groups, for the Spitzer group and then for the SOFIA project, meant when I was getting ready to graduate, it was right before Spitzer launched, and it was all very kind of carefully timed. I had it timed so that I graduated just before the launch of the telescope, and that way I could transition right from doing my thesis to doing the in-orbit checkout of my fine guidance sensor camera on board Spitzer. I had to really be available full-time for that for a few months to support the checkout. So as soon as that finished up, it turns out there was another job opening up on a new space telescope that NASA was about to start building. And this was called the Wide Field Infrared Survey Explorer, or WISE. And I ended up working as the deputy project scientist on that mission. So it just all kind of worked out very nicely.
Well, I think in hindsight, a lot of scientists say that it looks like when they look back that they had this plan lined out from, day one. But I think for you, you really did some planning to get all these pieces to fall into place, which I think is fantastic that you ended up at NASA with this wonderful position doing exciting research. And I want to hear more about it. So Amy, can you tell us more about one of these projects that you're working on right now that you are the most excited about?
One of the cool things about working on these projects is you really never know what you're going to find. I mean, you start off doing an experiment thinking it has certain specific scientific goals and objectives, and then it turns out that sometimes the research just leads you in a new direction entirely. And that is one of the most exciting things that can happen in science.
Definitely.
It's sort of the unexpected. I mean, it's just when things don't turn out exactly the way you expect, but they turn out even better, then that can be really fun. So in this case, the WISE mission is an all-sky observer. It's basically a spacecraft that is designed to survey the whole sky at infrared wavelengths, and it is able to do so very rapidly. The principal investigator of the WISE mission is Professor Ned Wright at UCLA, and he was always a really great role model and inspiration to me because he really came up with something that filled a specific need in the astronomical community. It turns out that the sky had not been observed at these wavelengths, the whole sky, not just little pieces of it, but the entire sky, hadn't really been observed in infrared wavelengths since the early 80s.
Wow.
And, of course, the one thing that's really changed since then are the detectors, the cameras. And as I mentioned, we started off with single pixels at infrared wavelengths, single pixel cameras. Mm-hmm. Now we've moved to megapixel cameras. So Ned figured out a design that was basically able to kind of capitalize on that incredible improvement in technology and use it to very rapidly survey the sky with huge sensitivity improvements over the prior mission from the early 80s. So the original scientific objectives were to find ultra-cool stars, a type of star that's called a brown dwarf. It's sort of halfway between a star and a planet, and very, very bright, luminous galaxies that shine brightly at infrared wavelengths. But it turns out the telescope is also really good for another thing, and that is for looking at asteroids. And that's because asteroids are actually very bright at infrared wavelengths, even though they can sometimes be extremely dim and faint to a visible telescope.
Interesting.
Yeah, this telescope turned out to be very, very good at spotting asteroids, lots of them. Even more than just finding them, it was able to learn about their physical properties, how big they are, how reflective the surfaces are, what kind of properties do the surfaces have, are they rocky or are they dusty, things like that.
So was it alarming when you were finally able to sort of see what was out there? Were there more asteroids than you expected?
That was one of the first things we wanted to ask is how many asteroids are there exactly? And you would think because we can see things at the distant edges of the universe, we can see these galaxies that are hugely far away, that we would know everything about our solar neighborhood, our solar system. Mm-hmm. But it turns out some very basic questions are actually surprisingly hard to answer. And one of the first things we looked at is could we use our sample of asteroids to extrapolate the population of asteroids and figure out how many there are and what are their sizes and what are their orbits like. What we found after using our sample is that there are actually somewhat fewer asteroids than we expected, and that's the good news.
Yeah.
This is in the near-Earth asteroid population, I should clarify. These are asteroids that make relatively close approaches to the sun, so we call them near-Earth objects. That includes both asteroids and comets.
Gotcha.
And what we were able to do is basically set some limits on how many we think there are. And we found that indeed, as I mentioned, there are somewhat fewer than previous projections. But then we found some other interesting facts. Like we found that when we considered the population of potentially hazardous asteroids, these are asteroids that make particularly close approaches to the Earth,
Not that any of them are likely to collide with the Earth anytime soon or anything like that, but just these are the populations of great interest. We found that when we look at this population, about 25% of them have been found at sizes down to about 100 meters in diameter. And we also found that when we considered those with the orbits most like the Earth, the ones that have the lowest inclination or tilt relative to the plane of the solar system, that there were slightly more of those. So that was an interesting result, and we're looking forward to basically gathering more data to see if we can find out anything else.
Well, very cool to hear a little bit more about your work, Amy. And I think this is really exciting and something that the public is really interested in. Well, I know there's all the sort of science fiction movies and sort of doom and gloom prospects of, is an asteroid going to hit the Earth? What would we do? How would we survive? And what would happen? So do you get a lot of questions from the press related to these things?
Well, I think it's natural to be curious about asteroids because we know that they certainly have impacted the Earth in the past. Human beings are basically here in some sense, indirectly because of an asteroid, in the sense that this is what ended the age of the dinosaurs and led to the rise of mammals and eventually to human beings. So that curiosity is very understandable. The good news is that one of the things we were able to verify with our WISE data is that the really large asteroids, the ones like the dinosaur killer, 90% of those have been found by the worldwide community of observers all over the place. And that's great, because now we know where most of the really, really big ones are. And these are the things that really would be capable of causing global extinction events. So we have found almost all of them, and we are tracking them, and none of them pose a collisional hazard. Now, for the smaller objects, we find that, as I mentioned, about only 25% of them have been found down to the 100-meter size scale. And when we look at sizes smaller than that, the fraction of objects that have been found is considerably lower. So we still have a lot of work to do to find and characterize the asteroids that get reasonably into the Earth neighborhood, reasonably close. But we're making really good progress. And the other important thing is that the warning systems are basically in place in the sense that when we find an asteroid or when we find something that we think is a new asteroid, there is a centralized bureau that we send the observations to. It's called the Minor Planet Center. And then once the Minor Planet Center receives the observation, they very quickly and automatically go and check to see whether or not these observations are associated with a previously known object. Or if it is thought to be new, then they quickly send it out to the worldwide community of observers for follow-up. And that includes both from amateur astronomers as well as professional astronomers. And of course, simultaneously, as soon as we find a new discovery, here at JPL, we have the Near-Earth Object Office that basically goes and calculates whether or not there are any impact probabilities at all in the next 100 years. Mm-hmm. So that all happens automatically. And what we're trying to do now is expand our sensor network so as we can gather more data, we can feed it into this automated system so that we can keep track of everything. So that's what we're working on now.
Well, that sounds phenomenal. And it's nice. Myself and our listeners, I know, can rest easy. You guys sound like you have it all under control, a great process in place. And I think so far we've really made your journey through science and your current position sound like a great adventure. It sounds like you've had so many exciting successes along the way. But I know there are dark days in science too. And I think every scientist has gone through struggles, challenges, and failures along the way. So Amy, can you take us back to a point in your career where you had a major failure or you were really struggling with a difficult problem? And tell us what happened and how you got through it.
Oh, yeah, you're right. For every success, it seems like there's about 3 or 4 failures along the way.
Right. That's a good ratio.
And that's where that persistence comes in again, to be able to get through it. So when I was working on the Spitzer Space Telescope on the Fine Guidance Sensor, we had a camera chip in there, a very tiny camera chip, that had to be connected to the rest of the housing of the camera using a fairly exotic material called molybdenum. And the reason for this is that molybdenum has a particularly good thermal property to it. It allows for the expansion between a silicon camera chip and the aluminum housing. It was a way of basically kind of matching the expansion rates because, as everybody knows, when you cool down a bottle of water, it expands, right? As it freezes, it becomes ice and it actually grows. Well, most materials shrink as they get cold, but they shrink at different rates most of the time. So this particular plate that we mounted the camera chip to had to be made out of molybdenum, as it turns out, so that we could compensate for the fact that the chip and the aluminum housing expanded at different rates as they got cold. The thing is that when we made this molybdenum plate, we had tried really hard to make sure that it didn't have any sharp corners or edges or anything like that would accumulate stress. Because as things shrink down when they get cold, you can have stresses build up in the part. And we didn't quite have it right on the first try. So we had gone through a vibration test. One of the things we do when we prepare something to go into space is we have to check that it can withstand the vibration environment of launch. And the rocket is incredibly violent. It really shakes things around. So what we did is we basically took the instrument and we put it on a giant shaker table, and you shake it really hard, just like it will experience on the rocket.
This sounds awesome. I want to see it.
Yeah, it's pretty nerve-wracking, I have to tell you, because you're just hoping and praying that the thing survives.
Yeah.
When we got it back to the clean room and we were able to take it out in the laboratory, we were doing a final inspection, and it looked like everything was going to be fine until the contamination engineer, who was looking for any sort of dust or debris on the instrument, came out and he said, "I found a metal flake."
Oh, no.
And I said, "That doesn't sound right. That's not supposed to be there." And sure enough, we went back in and we carefully inspected it. And we realized that the molybdenum part had cracked. It had developed stress. During the vibration test, there was a turn, there was an angle in it that was just a little too sharp. And unfortunately, the part developed a stress fracture right there. And there were metal flakes all over the place. So clearly that wasn't going to work.
Right.
And I just remember this horrible sinking feeling because I thought,
back to the drawing board.
oh, and we were so close. It was really, really, really upsetting. Then I had to learn way more about molybdenum than I ever wanted to know or ever thought I would ever need to know. And we really had to go in and start to understand the detailed material properties. Why had this particular part failed? Was it a combination of the material, the design? What exactly had caused the stress fracture? Because, we didn't want to do it again and then have the same result. In the end, we wound up doing a lot of work with a material scientist and with our mechanical engineers to try to crack the mystery. It turned out we were using a less perfect batch of molybdenum than we should have. This particular molybdenum needed to be higher purity, so we had to go back to the drawing board literally and go right back to the source of the material and rebuild the part from scratch. And then also just not use those sharp angles. That turns out to be a bad idea. Eventually, we tried a couple of iterations on the design, and it was a lot of scrambling. We had to really work fast because, of course, when you're building things for a spacecraft, you are on an incredibly tight timetable. You've got to make it to launch. And we were able to do it. We scrambled everybody together. I still have these wonderful electron microscope photos of this piece of molybdenum showing the just tiny little fracture inside of it and what it looks like at very high magnification. Eventually, we came up with another design for the part. And the next time we went to the shaker, it was still nerve-wracking. We were really sweating bullets, but this time, no metal flakes, and it worked.
That is an incredible story. So how long is this testing process? So like say you put it in the shaker, how long do you have to wait on the edge of your seat to see if the part's okay?
Well, in this case, this is a cryogenic instrument. That means because it's an infrared sensor, we're looking for heat outside in the distant universe. That means we have to keep it cold, very cold. For Spitzer, it had to be about 1 degree above absolute zero. That's very, very cold.
Wow.
So when we did the shake, we actually had to shake it inside of a giant thermos. It was actually mounted to the shaker table. It was a very complex experiment. And because it had to be mounted inside this thermos bottle, essentially, while we were shaking it, you can't see it.
Oh, no. That's even worse.
Yeah. So basically, you put the thing in the bottle, you evacuate all the air, get it cold, and then you put it on the shaker table, go through the shake for 10, 15 minutes, something like that. And it sounds really, really loud. Mm-hmm. And you just sort of sit there and hope, oh boy, I hope this doesn't break.
Right.
I mean, you can't see anything. So we were not, in this case, able to really get any information at all. We had to wait until we could get it off the shaker table, warm it up, open the thermos, take the instrument out, bring it back to the lab, and then be able to inspect it. So we had to wait several days until we could see what had really happened. It was definitely nerve-wracking.
That sounds like a tense couple days. Amy, wonderful to hear how you turn this difficult situation into a success. And I think that's something that scientists excel at. I mean, you're in these high stress situations in a lot of cases, whether you're applying for grants, whether you're doing a high stakes experiment, things like that. And I think a lot of scientists are able to just take those moments. You might have a failure, but you're able to turn it around, work quickly. And I think the team is a big part of that. So can you chat a little bit about what the team dynamic is in your group at NASA?
Well, this is, I would say, probably one of the things that, other than the subject itself, really makes science worth doing, and that is the people that you work with. In my case, I'm really lucky. I'm working with a great group. They're really wonderful people. They're all extremely smart, of course. That goes without saying. Mm-hmm. But they're also really nice, fun people. They're very dedicated and very loyal. And we've had a really good time working together. I really have a lot of respect for my teammates, and I'm so glad that I get to work with them. It makes a difference if you really like the people you work with.
Absolutely. I think you spend so many hours with these people every day. It's definitely a great idea to choose people who you get along with, who work well together and who are dedicated to the cause, which it sounds like your team is there. And now, Amy, we talked about one of your tough times. Next, I want to give you a chance to talk about a success story. So can you share one of these successes with us today? And it can be a big success or even one of these little wins along the way recently.
Well, I would say sort of the big, tall tent poles when you work in the space business is when a mission launches. That's obviously kind of the big moment.
Culminating moment, yeah.
Yeah, when you finally do all this work and you see your experiment stuck on top of this giant rocket is a very, very nerve-wracking moment, I would say. But the payoff is when the launch is successful and you see the instrument deploy. And then in the case of these telescopes, to start to get back the images, it's really amazing. These telescopes are our eyes on the universe. They see things that we can't see. So in a sense, they're part of us. And I think for me, getting to see some of the first images coming off of the missions that I've worked on, it's just mind-boggling. It's amazing to me how well it works. And I guess in a way, it's very hopeful because I think if all these thousands of people can work together and do their job so perfectly that you can send a piece of machinery up into space in this hostile environment and then return these beautiful images, that says something really good. We can work together and get good things to happen.
Absolutely.
It's just a matter of the willpower to do it. That to me is a very hopeful thing. And one of the other things, though, that I personally really like seeing happen is our students go forward. That's just incredibly satisfying and really fun to watch. I don't teach classes working at JPL. None of us do. But we do have student interns who come and work with us for maybe a semester or for a summer. And one of my favorite things is just watching them. They come and they work with us for a while. But then it's really fun to see what happens to them next. They all go on to do really cool, interesting things and become these just very interesting, smart, powerful people. And I love watching that.
Definitely. I think as a scientist, you have great opportunities to get a nice balance. I mean, a lot of scientists are able to do research they're really excited about, but also share it with the next generation of scientists. So wonderful to hear that you value mentoring and working with these students, and great to hear that you have that opportunity at JPL. And we've talked a little bit about your research, and we talked in the beginning about some of the stuff that you do outside of science as well. And I know one of the things that a lot of scientists enjoy doing, but perhaps are hard-pressed to find time sometimes, is reading. And I know I'm myself always on the lookout for book recommendations. So Amy, I'm going to ask you today, can you recommend for myself and our listeners a book that you have really enjoyed that you think we should check out?
Well, of course, I'm a huge Star Trek nut, but that's not what I'm going to recommend today. The book that I've read many times over the years that I really enjoyed is I, Claudius. That's a really interesting book, and it's about the Emperor Claudius, and it's by Robert Graves. If you like Roman history at all, this is kind of a personalized way of learning about it. It's a fictionalized autobiography written by Claudius, and it's a lot of fun. It's really interesting.
Well, that sounds like a cool book.
Being interested in mythology as a kid, this is a really great way to learn about it, and it kind of makes it personal.
Definitely. I know I'm one of these people, I'm interested in history, but I don't like reading history in a nonfiction sort of way. I love it when people wrap it in a story. So this sounds like a great read. So I will put it out on our website for our listeners to find. And we've chatted a little bit about your career and where you've been over the course of your career. And I think one of these opportunities that scientists get that they really enjoy about the job are some of the chances they get to travel. So can you think back on all the places that you've been throughout your career, Amy, for science, and tell us about your favorite?
That is one of the things as a scientist. We do travel a fair amount, either for field work, in the case of astronomy, to go to various telescopes, or to attend meetings and talk to other scientists and see what's going on. It's really important that you do go to these meetings as a scientist because it is such a global enterprise, and we have to have a way of keeping up with it. Things are changing so rapidly. So we do a lot of travel, and we have collaborations all over the place. To me, one of the favorite places I've been is probably Hawaii. That sounds like a cliche. Of course, everybody loves Hawaii, but the Big Island of Hawaii in particular is very special to me. I first started going there for a conference on infrared detectors, and it became clear that this is such a unique place. It's got a wonderful mix of the oceans, and of course, I love marine biology, and I'm a scuba diver, but it also just has the geology that's pretty fabulous, and then, of course, the biology is incredible. It's home to so many endangered species, and it's such a great example of adaptive evolution, where you have individual birds that came over long ago, and then they quickly evolved into many different species, just from one single ancestor. That is really cool.
Definitely. And I know I myself am a biology enthusiast as well as a scuba diver. Can you tell me, what is the coolest thing you've ever seen scuba diving?
Oh, my goodness. It's so hard to choose. There's so many things. I love it. One time I was in Hawaii scuba diving for vacation, and I heard whales underwater.
Oh, wow.
That was cool.
That's pretty cool. Did you ever get to see them or did you just hear them?
I've seen them from the surface. I've never seen them underwater, but I have seen dolphins while scuba diving underwater. And that was also just really, really amazing and surprising. We were just tooling around near the bottom of the reef, and I turned around and a pod of dolphins swam by. And it was just mind-boggling. They're so fast.
That is phenomenal. Wonderful to hear about your experiences traveling in Hawaii. Great place to pick as your favorite. And Amy, we chatted a couple times throughout this conversation about the people that you've encountered in science and even the team that you work with today. And I think the people that you get to work with as a scientist are one of the things that makes the job really fun and a great career. And I think there are some stereotypes about scientists out there, and we hope to break those on our podcast. So I love showing the human and fun side of science because I think scientists are people too. I mean, we're very serious, very passionate about our work, but we like to have fun and enjoy each other's company. So can you tell us today about a story, maybe one of these quirky traditions that you've experienced in science or just a funny memory?
Sure. One of the things is when you work in a lab, of course, you have to be very careful about observing all the protocols. And in this case, we had an anteroom to one of our clean rooms that we work in. And this was a kind of an outside area where people would sit around and do, work. And it was not a clean area or anything like that. And there weren't any chemicals or anything like that stored there. It was more or less an office space just outside of a laboratory space. And they had this cabinet that had a really intimidating sign on it. And it said, absolutely no food at all. So if you open the cabinet, that's where all the snacks were. So
it was the deterrent sign to...
Yeah. So, I mean, it was perfectly safe to have food in there. It was not a working lab area or anything like that. But yeah, I just thought that was funny. And so ever since then, it is kind of true. Having snacks is very important. So in our office area, we have a nice big common workspace room, and we have a snack table.
That is so funny. I think it's hilarious that you brought up the snacks because when I was in graduate school trying to pick which laboratory I wanted to ultimately join after a couple of rotations, I ended up picking the one that was not a wet laboratory, a bench lab, because I could eat snacks at my desk. Like this was a deciding factor for me. So funny that you mentioned that. Wonderful to hear about one of these traditions, one of these sort of sneaky hidden secrets in your laboratory where no one would find your snacks stashed away. I love it. Now, Amy, we've chatted about some of the people that you've encountered over the course of your career and also some of these great research questions that you've been able to answer. And I'm curious about what is one of these big questions that's still in your mind that you have not yet had a chance to tackle. I know as an astronomer, there are a lot of things standing in the way between you and all these questions you want to answer. Things like funding, staff, technology, feasibility. If we took away all of those restraints and restrictions, what is the question you want to answer?
Well, the question that I'm working on right now is basically how many asteroids are there, and are there any that are possibly heading our way? So I guess that's sort of the one that I would like to answer in the immediate term. That's sort of a kind of a practical thing. We'd really like to be able to expand our capabilities and find more asteroids. That's the one I'd most like to do now. In the longer term, I think questions of sustainability on the planet are very important. And of course, the asteroids are just one small part of that. The larger question is, what do we need to do to be able to live on this planet for a long time into the future sustainably? And I guess the reason for that is, as an astronomer, now we know that there are lots of planets out there. They're everywhere. As a spacecraft builder, I also know that it's really hard to get to any of them. I mean, it's very hard to even get to the planets closest to us in our solar system. Really hard. And I guess I think that that sense of perspective means to me that the most pressing question for us is how are we going to make life good here? And that's the one I would like to answer.
Well, I like that question, almost instilling a sense of urgency based on your perspective, knowing how difficult it is to find a new planet. We have to take care of what we have and we have to find a way to make it work. I love it. Great question for myself and our listeners to think about. And I think over the course of your career as a scientist, not only do you get to work on these exciting research questions in your mind, but you also get to meet a lot of inspiring, brilliant people who are great sources of advice. So can you share with us today, Amy, what you would consider the best piece of advice that you have ever received?
I think it was really from my mom, and she basically just said, hang in there and don't quit. That was the best piece of advice.
Short and sweet. I like it. Well, Amy, wonderful piece of advice and great advice for our listeners out there. Don't give up, listeners. Is there any other last piece of advice, Amy, or maybe one last piece of inspiration that you want to leave us with today?
I would say it doesn't matter whether you pursue science professionally or not. Just make science a part of your everyday life, because if you do, there's so many wonderful stories out there to learn about, and it's something you'll love every day. Just learn about the universe around you. It's so much fun.
Definitely. I agree. Well, I love this encouragement for being curious that you're giving our listeners. I think this is key. And I think you appreciate what's around you the more you know about it. So great note to end on here, Amy. Can you now tell our listeners how they can reach out if they want to learn more about you or your work?
I'm on Twitter, and so you can find me at Amy Mainzer on Twitter. That's probably the best way.
Fantastic. Well, listeners, follow Amy on Twitter. And Amy, thank you so much for joining us today and sharing a piece of your story.
You're very welcome. Thanks.
Well, it was a pleasure to chat with you. And listeners, thank you all for joining us today. We'll see you next time on another episode of People Behind the Science. Your voyage to the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to seeing you next time on People Behind the Science.